What is chemical equilibrium? Well, you're going to learn today that chemical equilibrium exists when you have a reversible reaction. A reaction goes forward and reverse, and the forward reaction rate is equal to the reverse reaction rate. Let's use this as an example. Let's say we take nitrogen dioxide, and if you see nitrogen dioxide is a brown gas, and so this is a brown gas, and this into dinitrogen tetroxide is a colorless gas. So we have a colorless gas here and a brown gas here. If they're put in a reaction vessel over time, you see at the very beginning we have all nitrogen dioxide. Then here we have a mix, and here, if you notice these last two vessels, this would be a molecular representation of the fact that we've reached chemical equilibrium. If we look at the number of nitrogen dioxides, there's 1, 2, 3, 4 of those, and that is consistent in the next one. We have 1, 2, 3, 4 nitrogen dioxides there. And if we look at the number of dinitrogen tetroxides, 1, 2, 3 of those, 1, 2, 3 of those, that is consistent as well. So when your concentrations are constant, and that means you've reached a state of equilibrium. The reaction is still occurring, forward's going forward, reverse is going reverse. The amounts do not change because of that, but you do have equal amounts. Here's what that reaction would be written in reverse. Now, if you write a reaction in reverse, we're going to learn how to write something called a K, which represents the equilibrium constant. That would actually be the reciprocal of the other K, of the K for the forward reaction. This is what that K would look like, and if we want to think about this reaction. If you start with it in reverse, if you start with a colorless gas and with just a little bit of the nitrogen dioxide that's colored, generally you see, gradually see more of that appear. And then here it becomes more brown, and there's more dinitrogen. Here you have a very brown mixture, and there's a lot of nitrogen dioxide. Now, any of these could be an equilibrium mixture because equilibrium is dependent on your temperature. So you can shift equilibrium based on temperature. So let's say we want to write our equilibrium expression for this. So the way you write an equilibrium expression, it's a capital K, and it's always products. So this would be dinitrogen, because we're writing it this way, dinitrogen tetroxide on the top, over reactants, the nitrogen dioxide on the bottom as your denominator. So it's products over reactants. Now, the other thing about writing a K expression is the coefficients are important. Your coefficients become exponents. Now, we have a coefficient of 2 in our reactant, so we put a 2 there. And there's a 1 there, so there's an understood 1 for the products there. So this is how that looks. So there we have the K is equal to the concentration of N2O4 over the concentration of nitrogen dioxide squared. And here we see the reaction going in reverse, where we have the brown going to the clear, but equilibrium could exist at any of those situations. That depends on the temperature we've chosen. So let's look at another situation. This is a reaction where we have carbon monoxide and water reacting to form hydrogen and carbon dioxide. Now we start with equal molar quantities of of water and carbon monoxide. So their concentration is the same. So as the amounts change, I should say everything is changing equal amounts because everything's 1 to 1 here. So we start off with all the reactants and none of the products. But gradually the amount of reactants change, the amount of products increase, and the rate of increase and decrease are the same because the slopes are the same. And at one point the concentrations remain constant. Now notice when those concentrations are constant, that's equilibrium. So the rates are equal. They're forming the reactants. Now this really should be a arrow going in 2 directions, one going forward, one going reverse. We're forming hydrogen and carbon dioxide at the same rate we're forming water and carbon monoxide. So that is a state of equilibrium, and at that point those concentrations are constant. Notice where those concentrations are not equal, but they are constant. Let's look at one more example. This would be the reaction of nitrogen and hydrogen forming ammonia. Now this time we're just starting with the 2 reactants, nitrogen and hydrogen, and we see the nitrogen and hydrogen are here. This is a nitrogen, that's a hydrogen, and notice there's no ammonia to start with. Gradually those amounts go down, the ammonia goes up, and at this point we reach equilibrium when those concentrations start to remain constant. Now the important thing, another thing to think about is these graphs could vary. You could start with these lines at any point in time, but wherever they reach and they level out, that's going to be an equilibrium point. That's where the rates of the forward and the rates of the reverse are going to be equal. Let's look at another example. Now this graph is different from the previous ones, and this is similar to the one on your note sheet. You have reaction rate here on the y-axis. You have a forward rate and reverse rate. Now the reverse rate is occurring very slowly because there's no products at the very beginning of the reaction. The forward rate is the fastest initially because at the very beginning you have a high concentration of the reactants. But notice the forward rate decreases, reverse rate increases, and at some point they meet, and the forward rate is equal to the reverse rate, and you guessed it, at that point we have equilibrium. Now, once again, we should change that to a two-sided arrow. Let's look at how this would appear if we were trying to look at it at a molecular level. At the beginning, we have more of a mixture of the carbon monoxide and water. You see carbon monoxide there, water there. If we count those, there's 1, 2, 3, 4, 5, 6, 7 waters, and 1, 2, 3, 4, 5, 6, 7. So equal molar amounts of carbon monoxide and water. Those amounts change. So here is the time initially. Here we see it start to change, and these two I believe would be equilibrium. If we look closely, we're going to have equal amounts. We count the products, and notice there's still reactants present, carbon dioxide and water. We have 1, 2, 3, 4, 5 carbon dioxides, 1, 2, 3, 4, 5 carbon dioxide, so that has remained constant. We'd expect the other reactant, since it's a 1-to-1 ratio, to be the same. 1, 2, 3, 4, 5 hydrogens. 1, 2, 3, 4, 5 hydrogens. That is constant. Now let's look at the reactants. The water, we've got 2 water molecules here, 2 water molecules there, and then also the only one I didn't circle was a carbon monoxide. We see there's 2 carbon monoxides here, 2 carbon monoxides there. So this is equilibrium. The concentrations are constant in those last 2 time frames. Now, what else would this equal? So let's define equilibrium. Equilibrium is a condition in which the concentrations of all the reactants and the products in a closed system cease to change with time. So at equilibrium, the rate of the forward is equal to the rate of the reverse. Now, notice at equilibrium, there's no further net change that can be observed because the changes in one direction are balanced out by changes you see in the other direction. So the reaction is not really stopped, even though we don't see a change. Now, the other thing is the amounts of the reactants products are constant. They're not necessarily equal. And let's look at a couple of different situations. We have 3 different experiments. Each one we're starting with different initial concentrations. Now, this is a reaction we talked about earlier with nitrogen and hydrogen forming ammonia. Here we start with just the reactants, no products. They reach these equilibrium concentrations. Those equilibrium concentrations are plugged in our K expression. Notice it's products ammonia squared over our reactants nitrogen times hydrogen, which is cubed because that's a coefficient from the balanced equation. We put these numbers into this and we end up with this K value. Then we do the same experiment but start with just the product. The product goes in reverse, forms the reactants. We end up with these amounts. Plug these into K and once again we end up with the same value. And then we have a third scenario where we start with a mixture of all the substances. We end up with these at equilibrium, plug these in, and once again we end up with the same K. You end up with the same K as long as you have the same temperature. Temperature is the only factor that will change K. So remember, K is equal to products over reactants. That's our equilibrium constant. The rates at forward equal to rate of reverse. Any of the coefficients from the balanced equation. And K is dependent only on the temperature of the system. A couple things to notice. Now we're doing this, usually we're talking about concentration. Concentration refers to an aqueous system, or it could talk about a gaseous system. So those are the 2 systems we'll use in K expressions. We will never use a solid or liquid, so the liquid state will not be included and the solid state will not be included. So those will never be written in your equilibrium expression. They may need to be present in order for a reaction to occur, but do not write those in your equilibrium expression. So if you were to write a K for the reaction we saw earlier for our colorless gas going forward to the brown gas, this is how this K would be written with the nitrogen dioxide squared on the top and the colorless gas on the bottom. So let's see if you could write the equilibrium constant for the combustion of propane gas. You can stop the video and see if you can do that. So hopefully you came up with this balanced equation, because you need a balanced equation first. Then you plug the values in and got this K. So check and make sure you got that. If not, you can go in reverse and try it again. And a couple things about K. These C indicate that we're using concentrations, that C right there. So we're using basically molarity, which is moles over liters. And it's a unitless number is what you usually express K in. So what is the range of equilibrium constants? Let's say you have a big K. What does that mean? Well, basically it means you have a lot of products, because that's on the top, over a few reactants. So you're dividing a big number by a small number. Now I'm sorry, they're starting with a small K, so that's the opposite. We have very few products, but a lot of reactants. So we're dividing a small number by a big number. That gives us a very small K. Now a big K, so that would be a negative exponent. Now a big K would be when we're dividing the products, which is a big number. We have a lot of products, so big P over a very small reactant. So I'm going to divide a little small r there. So you divide a big number. So here we did the opposite of this on the small K. We divided a small number of products by a big number of reactants. So the large K is the opposite. We've got a lot of products, so you're going to have an exponent with a very large number. And the intermediate means you have some type of mix in there. Let's look at a couple of examples here. So we've got these two reactions. This is nitrogen oxygen forming nitrogen monoxide. Notice this is a very small number. So that would be an example of a small K, 10 to the minus 30th. Then you look at the other reaction where you have nitrogen hydrogen forming ammonia. This is a big number. So this is our example of a big K. And this is a small k. Small k indicated by the negative 30, big K indicated by the 10 to the 8th. And finally, you could also use pressures in your equilibrium expression. So you can use partial pressures. So that means, because we think about if you have a higher pressure, you basically have a higher number of particles in a certain volume. So you do it the same way. You put your products on the top and your reactants on the bottom, but these will just be in pressures. And this is how that expression would look. And so this would be called a Kp instead of a Kc. So you're putting pressures in instead of molarity. And the relationship between Kp and Kc is expressed by this formula. So Kp, which is using a K with pressures, is equal to Kc, one with concentrations, times RT to the delta N power. Now R for this is 0.0821. That's 1 liters atmosphere mole K, and T is the temperature. Hopefully you guessed it, in Kelvin. Now what is delta N? Delta N means a number of moles of gas product minus the number of moles gas reactant. So this is the last thing we'll do as an example here. Let's say we have this reaction. Nitrogen plus hydrogen forms ammonia. What would be the delta N for this? Well, you do products minus reactants. So basically it would be 2 minus, when I add these together, 1 plus 3. So 2 minus 4 equals minus 2. So that would be the N for this. That's it. Thanks.